Today we're going to solve the Schrodinger equation for a free particle. Now you might think that free particles should be the easiest solution to the Schrodinger equation, but in fact there's a lot more to it than you might think originally. So we set up our Schrodinger equation. There's no potential. Potential is setting equal to 0. So it's minus h bar squared over 2m, second derivative of psi with respect to x is equal to e psi. I'm going to change variables. I'm going to use the variable k to represent the square root of 2me over h bar. It's a little bit simpler looking differential equation. But we can immediately see what the solutions to that differential equation are. We'll write it as psi of x is equal to a e to the I kx plus b e to the minus I kx. You might remember that when we did this for the particle in the box, this is essentially like the particle in the box when it's inside the box. We use sines and cosines, but in this case it turns out to be a little bit more revealing if we write the sines and cosines as e to the i's rather than sines and cosines. I can also put a time dependence with this. Remember, as we said earlier, all I have to do is multiply by e to the minus I-e h bar over, I-e-t over h bar omega. So I can write this then psi, capital psi of x and t as a e to the I k, and I'm going to write this as x plus h bar k t over 2m plus b e to the minus I k x plus h bar k t over 2m. What this represents is a wave that's of a fixed profile. It's traveling either to the left or to the right, depending on how you look at this, or plus and minus x direction, at some constant speed. And this is the speed. The coefficient of t, of course, x plus vt, x minus vt. And the second term, of course, should be a, this should be a minus up here, sorry. It's minus vt, there we go. Okay, so this is a term traveling to the right, this is a term traveling to the left. Now here's the thing, since every point in a wave moves at the same velocity, the shape of the wave should never change. A term is going in the plus direction, B term is going in the minus direction. Well, let's make this a little bit easier on ourselves. Let's just use one term, and let's let k take on plus or minus values. That'll make it a little bit simpler. So I'm going to let k be equal to plus or minus the square root of 2me over h bar. And when k is greater than 0, the wave travels to the right, or in the plus direction. When k is less than 0, the wave will travel to the left, or in the minus x direction. Speed of the wave, as we said, let's call it the quantum speed of the wave, use of quantum. That we said is h bar magnitude of k over 2m, because that's the coefficient of t in my exponential equation. And I can write that also in terms of e as the square root of e over 2m. I want you to compare this, though, to what you know classically. Classically, we know that we're used to writing velocity as twice the energy over the mass. And so the prediction is that the classical velocity is actually twice as large as the quantum velocity. So that's telling me that the quantum mechanical wave function travels at half the speed of this so-called particle that we're representing. There'll be more on that later. That's just a distraction. Here's a bigger problem. Look at that wave function. It's not normalizable. Notice, I can do the following. Psi star psi dx from minus infinity to infinity is just giving me some a squared integral of dx from minus infinity to infinity, which of course blows up. That's not legal. So these separable solutions don't represent anything physical. It's not a physical state for a free particle. It tells me that a free particle can't exist as a stationary state. There's no such thing as a free particle with fixed energy. Nonetheless, we'll get some mathematical benefit from this solution, and we'll see that later on. I'm going to write the solution psi sub k of x in t as a e to the minus I kx minus h bar k squared t over 2m. If I want to look at this in the x frame, however, I can write this as 1 over the square root of 2 pi integral phi of k e to the I kx minus h bar k squared over 2m times t dk. So what we're going to do is we're going to represent our old C sub n, the coefficients of expansion. We're going to represent C sub n by the function 1 over square root of 2 pi phi of k dk. Why? Well, the reason is as long as we choose phi of k properly, we'll be able to normalize psi sub k of x and t. The wave function can carry a range of k's, and then, of course, carry a range of speeds and energies and so on. Of course, we recognize this expression as nothing other than the Fourier transform. In our case, we can write phi of k as 1 over the square root of 2 pi integral minus infinity to infinity psi of x and 0 e to the minus I kx dx. So for example, suppose we have a free particle that's located in a range minus a to a, and it's released at t equals 0 such that at t equals 0, psi of x and 0 is equal to capital A if the particle is between minus a and is equal to 0 otherwise. And what we want to do is let's find psi of x and t. So we can't just multiply by e to the minus I e t over h bar. What do we do? What we're going to do then is we're going to first, let's normalize psi of x and 0. To do that, I can say integral minus infinity to infinity a squared dx, and actually we're only going from minus a to a, that's the only place it can exist, is equal to 2a squared, which is equal to 1. It's got to be somewhere. So if I solve for a in terms of little a, I get that it's equal to 1 over the square root of 2a Now I've got to calculate phi of k. Well, to do that, I need to take a Fourier transform. And so phi of k is equal to 1 over k square root of pi times a, square root of 1 over 2 pi, 1 over square root of 2a, integral from minus a to a, e to the minus I kx dx. Of course, the integral of that is e to the minus I kx over ik, evaluated between minus a and a. And that's going to give me 1 over k square root of pi a e to the ika minus e to the minus ika, all divided by 2I, which of course recognize this is the sign. And so this is going to be 1 over the square root of pi times a sine of ka divided by k. So that gives me phi of k. And now, of course, if I want to put that in so that I can get the time dependence, let's move over here and do that. Psi of x and t then is equal to 1 over pi square root of 2a, integral minus infinity to infinity sine ka divided by k e to the I kx minus h bar squared k squared over 2m times t dk. Now, here's the bad news. That's as far as we can go. The only way we can do this integral is to evaluate it numerically. But you see, it's a useful operation. It shows you how the Fourier transform can be used in enabling us to normalize a wave function and get an expression for the wave function as a function of time. Now, psi of k is not a physically achievable state, and so we might say, well, why do we care about the velocity since we can't really achieve that state anyway? Nonetheless, it might be interesting just to see what we mean by this velocity and why it's half the size of the classical velocity. Let's go back to the notion of wave packets. Wave packet is a sinusoidal function which is amplitude modulated by phi, kind of like ripples contained in some envelope. The particle velocity corresponds to the speed of the envelope itself. We call that the group velocity. So we'll equate the particle velocity with the group velocity. But the velocity of the wave, like any point on the wave, is what we call the phase velocity. So the wave velocity, like any point on the wave, is what we call the phase velocity. As it turns out, the phase velocity is often expressed as omega over k. The group velocity is expressed as d omega dk, as you'll see. So it's not surprising that the two items would have different values. For example, if I talk about waves on a string, the group velocity and the phase velocity are exactly the same. However, water waves, the group velocity is actually half the phase velocity. So we might ask ourselves, what's the group velocity of a wave packet that has the form psi of x and t equals 1 over square root 2 pi, integral minus infinity to infinity, phi of k, e to the I, kx minus omega t, dk. Well, suppose phi of k is just a narrowly peaked function. Maybe it's peaked about some value k naught. If it's narrowly peaked about k naught, the integral will be negligible unless we're in a region near where k is equal to k naught. So what we'll do is let's expand the function omega of k about k naught. So I can write omega of k as omega naught plus d omega dk times k minus k naught plus higher order terms, and we'll just neglect them. Let's define S as k minus k naught. Then I can write psi of x and t as 1 over the square root of 2 pi, integral minus infinity to infinity, phi of k naught plus s, e to the I, k naught plus s, times x minus omega naught plus omega naught prime, which is d omega dk, times s, all times t. Yes. So at t equals 0, psi of x and 0 is just simply 1 over square root of 2 pi integral phi of k naught plus s e to the I k naught s plus k naught plus s times x ds. At some later time, we can write it as, at least approximately, psi of x and t, approximately at some later time, e to the minus I, e to the I, omega minus omega naught, e omega naught minus k omega naught k naught prime t times psi of x minus omega naught t prime 0. So the wave packet moves at a group velocity of d omega dk at k equals k naught, unlike the phase velocity, where the phase velocity is equal to just omega over k. So since omega is equal to h bar k squared over 2m, d omega dk is equal to h bar k over m. And so omega over k is equal to h bar k over 2m. So what that means is velocity for the group, B group, is equal to twice the velocity of the phase. This is, of course, this represents the classical velocity of the particle. This represents the quantum mechanical velocity of the particle, and that's where that comes from. So, just to make a long story short, the free particle is not such an easy case. It did bring us along and bring back Fourier transforms. You can see that they're useful and will be more useful as we go through quantum mechanics. What I'd like to do next time is to talk about bound and scattering states. We'll do some things like the delta function potential, and we'll do the finite square well, which are also very nice examples of one-dimensional solutions to the Schrodinger equation.